I will begin. Texas. Texas has got problems too. I'm thinking Tennessee maybe.
I would never live in Texas.
Yeah. Tennessee. Maybe I'll get a boat and just live on the seas. I don't know.
Gotta move it to Idaho.
Idaho. Oh,
I was about to absorb half of Oregon.
No, there's.
They got potatoes, right?
I live in Oregon. Everyone who's not from Portland is pretty solid.
Yeah, I don't know. Well, I will begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for the students, this class, and this chance we have to study your creation. Just pray that you would be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so today we will study electromagnetic waves in conductors. Now, so basically we're wanting to write down what are the Maxwell's equations in a conductor. All right, that's essentially what we're looking at here. And so in this context, we don't have we have free charge is the thing as a conductor, right? So all right, so basically our starting point is to go, okay, so the free charge current is, we're going to do Ohm's law, right? So the conductivity, sigma, times the electric field, all right? And so this means that Maxwell's equations are a little bit different than what we've had like last class, right? So we've got a source to deal with. So we have, let's see here, the divergence of the electric field is the free charge density divided by epsilon. The divergence of the magnetic field is 0. The curl of the electric field is minus partial B partial T. And the curl of the magnetic field is mu sigma E plus mu epsilon partial E partial T. So this conductor, right? This has permeability, mu, and permittivity, epsilon, all right? So that's not, that, the Maxwell's equations are modified by those as well, right? But we saw that last time in the linear media, but this time we've also got the free charge density to worry about. Okay, so let's see here. Let's work on this a bit. So what's the fundamental thing about the free charge density and the charge density? It's governed by the what?
H field.
The what?
H field.
The H field. Ah, very true, but no H field today. So good answer, very good answer, but more basic than that. Like what's one of the basic laws of physics besides Maxwell's equations? In fact, an implication of Maxwell's equations is this: conservation of charge, right? So we have that the divergence of the free charge density is equal to what? Minus the time rate change of the the volume, free charge per unit volume. So the divergence of the free current density. I keep saying charge. I may be saying the wrong thing. My brain's not working. But there you go. That's conservation of charge, right? So, all right, let's look at this. So we have the divergence of the electric field is, 1 over epsilon times rho f, right? But we also know that the electric field, by Ohm's law, is what? I can say that's the free charge density, free current density divided by sigma, right? And so this gives me 1 over sigma, the divergence of the free current density is equal to, 1 over epsilon times the free charge density. All right? But we know by conservation of charge that we can trade this guy for that guy, right? So what that gives me then is partial rho f partial t is actually equal to minus sigma over epsilon times the free charge density. You guys with me? Okay. I figured this out today. It can't be that hard. I'm not working with a full deck today, so, all right. Now this thing, you might recognize as a differential equation that we could have solved in calculus 2 by separation of variables, and the solution would just be the free charge density as a function of time is equal to e to the minus sigma over epsilon times time times the free charge density at time 0. You can see that the solution I just wrote down there solves the differential equation above. If you differentiate that, you get back minus sigma over epsilon naught, sigma over epsilon times that again, which is to say it solves the differential equation. And of course, if you plug time 0 into it, it works, right? So here, if we can rewrite this as per usual, minus t divided by tau, where tau is a time constant, right? And that time constant here would be defined to be epsilon over sigma. All right? And so in a typical metal, this is very, very, very small. What does this mean? Yeah, the diffusion is quick. So if there is any free charge, right, it dies off pretty quickly. It dissipates. Which means that actually Maxwell's equations are a little bit easier to solve than we first thought. You see, we can solve the quote-unquote steady state Maxwell equations, right? Just let time go on, and we're up against not this anymore, but essentially you can just, set this guy to 0 for basically t much, much greater than a time constant, which isn't that long, all right? Okay, so then this is still not the same problem we had last time, right? It's not that we're back to the problem we had last time. It is genuinely different. Like this thing right here, that's different, right? This term right here is really, not what we faced last time. All right, so I'm going to add something to my notes here because I think it's probably helpful for us to work this out. So you guys remember how we find the wave equation? It's all from which vector identity? Yeah, the curl. Very good. So I'll write it up here again for reference. Curl of the curl, I'll do it for vector field A, is equal to the gradient of the divergence of A minus the Laplacian of A. All right? So we take that, right? And we put Maxwell's equations into that, right? And what happens? So we get the curl of the electric field is equal to, minus the Laplacian squared of the Laplacian of the electric field, rather. So the curl of the electric field, that's just minus partial t of the curl of B, right? Which is minus partial t of what? Curl of B is mu sigma E plus mu epsilon partial E partial t, right? And that's all equal to minus nabla squared E. All right. If I haven't lost a minus somewhere. Okay, so that gives us what? That gives us nabla squared E equal to what? Equal to mu epsilon, right? Partial squared E partial t squared. That's nothing. We saw that last time, right? That's, yep.
Is this assuming that the free charge is a constant?
The free charge is 0. Yeah. So, yet we're still including the sigma j term. Don't ask questions. Well, it was the current density, not the surface density. All right. We showed it 0. So, all right. Probably a more nuanced discussion here would say we're working in a certain approximation or something. If I had to, Now you've made me question my life. Thanks, Shane. Good job. But so we got that term right, but we also got this term, which is plus mu sigma, right? Partial E partial t. And so there you go. That's not the same wave equation we had before, right? There's a new term, that first derivative term, that was not present before. Okay? And almost the same calculation will show you that the Laplacian squared of the magnetic field also solves mu epsilon partial squared V partial t squared plus mu sigma partial B partial t. So what do you have any kind of intuition about what we're up against here? Like, what does that do, adding that derivative term? What's it like?
A factor of time on all the exponentials.
Yes, very good. But how about, here's the analogy, by analogy, if I have m x double dot, right, equals to kx. You guys know what that's like the simple harmonic oscillator, right? What happens when you add there's a minus here, right? So minus, what happens when you do that? What's that? Yeah, it's a damping term. It makes the spring retarded, right? So the spring becomes retarded. And but like Sam was saying, it's going to introduce a exponential with a negative time argument, right? E to the minus t kind of stuff, right? That's the net effect of it, is that you get damped exponentials. And the same is going to be true for this. That's going to happen. So at this point, Griffiths pulls the solutions from the bright blue sky. All right. So I will do the same. Okay. So this is, what are the methods of solving differential equations? Use matrices. Whoa. Whoa. Guessing. Yes, guessing is the answer. So guessing. The Laplace transform. That's actually not unreasonable. But I don't introduce a vector Laplace transform. Although, Fourier transform, right? Whatever. If we went back to our earlier discussion, we probably could solve these by separation of variables. You could suppose a product solution, plug it in there, and work through it, and probably get to the solution if you wanted to that way. But I won't. But I think you could. But the solutions are this. So E tilde, and we're going to look at the ones that are, so this is not the general solution, this is just a solution, right? This is the plane wave solution in the z direction for propagation. And so EZT is like E sub naught, and I'll use this obnoxious notation, vector tilde, not in Griffiths, that's my addition to the stupidity. So that's a K, watch this, tilde. Notice the tilde here, and it's a capital, it's like a lowercase k. That's important because we will soon be writing lowercase k, kappa, k tilde, and also big K. So you're aware, don't be like me, taking notes, and a half hour into it realize that on the board there were K's and kappas, and I was just writing K, and I'm like, you know, like, that's the worst feeling. You've been like dutifully taking notes, and all of a sudden you realize two of the letters you thought were the same were different, and you're too far past it to fix it. It's the worst feeling. Okay, there are worse feelings, but anyway, that is the solution. And likewise, B tilde, ZT, is equal to B naught vector tilde e to the I k tilde z minus omega t. All right. Okay. Let's see if this makes sense. If we think about plugging either, let's look at the electric one, right? Plug that into the wave equation, what happens? Right, let's think about that. What's nabla squared E tilde, what's that look like? So this is a constant, right? So it pulls out. And then we basically have, nabla squared. Well, nabla squared, but okay. This is spatial nabla, right? There's only spatial derivatives in here, yeah? So, and this only has a z dependence. So it's really, in effect, partial z squared acting on this thing, all right? Where I've decided to call this theta per my usual custom of not writing that. Okay, so you twice differentiate it, what do you get? You get E naught vector tilde, what a mess. And I k tilde, right? Quantity squared, e to the I theta, yeah?
Would that be in z hat?
No. That's just regular z, not vector z. Partial z just kills it. I mean, like, basically the point is partial theta, partial z is just straight up I k tilde.
So I is included in it?
Oh yeah, I's there. There's also an I in the k tilde. K tilde is complex. Now, on the flip side, we are also supposed to have mu epsilon partial squared e partial t squared plus, so like I've written out notes, guys, at the moment where I was just working through Griffiths, but I'm somewhat dissatisfied with like the logical content. So what I wanted to do was just plug these solutions in and see what they force on us to see if I can understand why Griffiths is making the definitions that he is. That's what I'm doing. It won't take us long. What happens when we take the time to, so like we're going to have, again, mu epsilon E vector tilde naught pulls out, right? And when we take two time derivatives, the key thing is that partial theta partial t is what?
Negative omega.
Negative omega, but don't forget. Oh, you're right. I'm sorry. I'm including the. Oh, yeah, there's no I here. That's what you're asking me. Yes, thank you. I'm an idiot. I'm sorry.
That's what I was thinking.
Yeah, no, you're right.
The T derivative.
I'm sorry. Like, yeah, okay, so fair enough. So since I'm putting the argument I theta, the chain rule ends up, like, I have, the real question is, like, what's the partial of I theta, right? Sorry. I mean, that's what the chain rule is up against, right? Because the argument of the exponentials, I theta. I should have just lumped the I into the theta, and then we'd be properly confused. But, okay, so mu, epsilon, E vector tilde, two time derivatives. So we got a minus I omega quantity squared, e to the I theta, right? That's from the first term. And how about the second term? Plus what? Mu sigma, one time derivative. So we just have a minus I omega e to the I theta, I think. And there's still a, don't forget my E vector tilde, not, all right? Now these are equal, right? So since these are equal, what does it give us? We get, yeah, you get I k tilde, I won't simplify the I yet. I k tilde squared, right? Equal to mu epsilon minus I omega squared, right? Minus mu sigma minus I omega. Right? Square this thing, we get a minus k tilde squared equals to minus mu epsilon omega squared plus I mu sigma omega. Finally, I get k tilde squared is equal to mu epsilon omega squared minus I mu sigma omega. I am, oh, rats. I don't have the minus in Griffiths. Find my error. Like this is supposed to be plus. Say again, where?
So it's supposed to be plus mu sigma and then negative I omega.
Oh, yeah.
Where?
So when you have the bendy equal sign,
Yeah.
that version has a plus instead of a minus.
Oh! Thank you. So that makes this a minus and this a plus. And yay! All right, so this is an equation that Griffiths just writes down. All right. All right. All right, so in the interest of not being here until 6, let me... I wanted to go slow through this part because I wanted you to understand, because this, well, this is not all that matters, but we'll see here in a second. Nope, back. Whoa. Sounded like it was about to, like my van door, sometimes when it does that, it just goes back open, you know? Let's see here. All right. Come on. Oh, there it is. I will eventually catch up on the website. I have a bunch of lectures I need to post. All right. All right, so a lot of this we have gone through, right? I think we've reached like page 3 at the moment. All right. So we derived that we have the steady state Maxwell equations. As you see, I didn't put the details of what we just did on the board of the notes, but we just worked those out, right? Nothing too surprising there, but there it is. And then Griffith's like, oh, these are solutions, right? And then he says where K tilde must, I mean, I don't know if he says that or not, I'm saying that. But, so you see why that has to be, right? In order for this to solve the, let's call it the attenuated wave equation, right? In order for it to solve that, we have to have this particular relation on the complex wave number, K tilde. K tilde has to satisfy this jazz right here, where the mu, the epsilon, and the sigma are given, and I guess omega is also in some sense given. It's the source frequency of the wave, right? So that's not a property of the medium or anything. That's just like we've got a laser, you know, it's got a particular frequency, omega, so that's where that's coming from. But we wouldn't expect omega, we wouldn't expect the angular frequency to be a property of the media, you know? It's a property of the source. So Griffiths introduces, as I was warning, K tilde has actually got a K and a kappa. Kappa is the imaginary part, K is the real part of the complex wave number. Yep. And then he defines kappa and K to be this. There must be a reason, like, it's probably just like simple complex analysis, and I haven't played with this long enough. Like maybe if I played another half hour with the math, I'd see through it, but.
It's just the quadratic formula.
It's just the quadratic formula? It's just the quadratic formula.
He just solved for K tilde, I think. Wait, no, he didn't. Never mind. Maybe he solved for omega.
Just the quadratic formula.
That's all you need to do.
Just the quadratic formula. You know? Well, maybe. So you're saying just solve that for kappa, you solve this for K tilde, you take a square root. But the thing is, when you take a square root of a complex number, what do you mean by that? Have you guys had, well, Shane has had complex analysis, but have you guys?
You could make it doubly.
So how do you take the square root of like 2 plus 3i?
I mean, I has a square.
Yeah, what's the square root of I?
I don't remember.
E to the pi over 4. It's very simple actually. You just convert the number into the polar notation and divide the argument by 2. That's half the story, and then minus that is the other root. So you don't have much to learn, but this is something you'd learn in like the complex. Well, math 331. Very appropriate, right? Anyway, I'm not sure at the moment for shame where that came from. But he says those are definitions for K and kappa. Great. And I'm like, okay, what's the deal with K and kappa? So I took his formulas and I squared them and I added them together, to see what would happen. All right? And so the square root unsquares, and you get a +1 and a -1. Those be canceling. This is the same thing twice. That twice cancels that too, and leaves you with an omega squared epsilon mu, that. And then I brought the epsilon mu inside, and then I brought the omega inside, and then I multiplied half of that over through here to get rid of the fraction. And then there's easier ways to do this math, guys. This is why I wanted to show you and not write it out. So then I factored the omega mu out, and I'm left with this. And I'm like, oh, okay, well, come on. And then before we had, now I understand where this came from. This is a demand of the attenuated wave equation. This is the condition necessary for the complex wave number to solve, to give you a solution. Right? This is analogous to the characteristic equation in the sense of differential equations for our solution. It's like k tilde has to satisfy this condition in order to solve the attenuated wave equation. And it just so happens that if we define k and kappa as Griffiths has, those square together to reproduce this, which incidentally is that. And all right, so like the length of this, this is a complex number. Words. All right. Anyway, I'm sorry. I'm just on a. I'm still. There's something about the k and the kappa and the k tilde I don't understand yet, and it's bothering me. I was hoping in the process of talking to you guys I would see through it, but I haven't yet. So my apologies. I don't think there's anything deep I'm not saying here. It's just algebra. But so we have these solutions, right? And the thing is, if we now write it out as Sam predicted, e to the minus kappa z. This is the attenuation factor. That's based on the real part of the complex wave number, where that kappa is. We gave the formula for it just a second ago. All right. And so what does that do? What is the solution? What happens to the solution? Effectively, the amplitude is the thing that multiplies the imaginary exponential, right? And that is dying as z, as we go past z equal to 0. If we go into positive z, it's going to 0, right? So, assuming that the wave is before the conductor. Like for z less than 0, let's think about we're outside of the conductor, all right? And then at z equal to 0, we hit the conductor. As we go into positive z, our wave is traveling in the conductor. It doesn't do so for long, effectively, because this thing kills it quickly. And so this is why we say there's a quote-unquote skin depth. It's sort of analogous to the time constant, but this time in the spatial sense, right? The reciprocal of the real part of the complex wave number is the skin depth. And there was a formula for this a second ago. Yeah? The formula was this right here. So that's a particular, it's based on the permittivity, the permeability, and the conductivity of the conductor. That defines the skin depth. And also there is a frequency dependence, right? Apparently there is some frequency dependence. Different frequencies would have different skin depths. Yeah. For example, a gamma ray is going to get further into a metal than like a infrared one, I think. That's my intuition. It's like higher energy, greater penetration. It'd be funny if I was wrong. It'd be funny if I was wrong. It's the opposite? Oh my.
Bigger omega, but bigger kappa.
Oh.
Smaller.
There's like radio waves, or like our cell phones have service, and they can pass through walls. But even though it's not conductors.
So you think on the basis of,
The X-rays can stop black
huh?
holes.
But X-rays go through walls, and X-rays are higher frequency than, I think X-rays are higher frequency than. Am I wrong? Microwave,
Sure, you're
right? Yeah. But anyway, absorption and all of that's actually a very, very complicated, interesting question that is well beyond a simple discussion. Like, there's a lot to that. And of course, there's, the conspiracy of the 5G. We have to think about that. But anyway, sorry. I'm a bad son. All right, let's see here. Come on. So he says the skin depth is defined like this, and then essentially the wavelength, the speed, and the refractive index are defined by the real part of the complex wave number. Now, he doesn't really do anything with these, but there they are if you want to. I mean, the wave is dying in short order, so I don't know, like, it's not that interesting, I think, to look at this. Like, it's dying pretty quickly, but none of these things quite make sense either, right? Because it's not periodic. The amplitude is squashing to zero, right? So it's like quasi-periodic. It's like it's inside an exponential envelope going to zero. So what do any of these things mean? Well, it's just kind of a rough analogy to the usual thing. All right, anyway, so moving on. So Maxwell's equations place further constraints on our attenuated wave solutions, just like we did last class. The divergence of the electric field being zero, the divergence of the magnetic field being zero, they tell you that the complex amplitude can't have a z component. So the wave can only wave in the perpendicular directions to the direction of it's a transverse wave, all right? It's waving perpendicular to its motion, yeah. Transverse wave. So we might as well set the polarization in the x direction. And so that gives us this, all right? Notice it's attenuated by that factor right there. And likewise for B, all right? However, notice now, unlike our previous work, we don't have necessarily the same phase for E and B because they don't share the same complex. There's like, this is complex. So the phase is shifted. They're not in phase. There's a phase shift between the electric and the magnetic. And he introduces a notation for the phase. So finally, phi. You guys are happy, right? There's the phi. So big K, as I advertised, times e to the I phi is the k tilde, which of course, magnitude-wise, square root of k squared plus kappa squared, which incidentally is that, all right? And there's the formula for the actual, phase. And so if you look at this equation star and just study the amplitude being, complex amplitudes being equal, it gets us this equation here, which shows you that the magnetic phase and the electric phase, they're not equal, they're like related by this shift. The magnetic minus the electric is equal to the phi. And so what that means is that the magnetic field lags behind the electric field. If you look at page 421 in Griffiths, he has a lovely picture of this, all right? In contrast, in free space or in a linear media, the electric and magnetic wave are in phase, and they're, just it's nice, neat, transverse wave. And the amplitude stays what it is, right? Energy is conserved. It just goes on and on forever, right? Electromagnetic waves have infinite range in free space or in a perfect linear media. But in a conductor, well, the range is kind of short. So there's the real McCoy. These are the real solutions to the attenuated wave equation. Now, so the next thing, of course, is you want to think about. So the next thing you think about is you've got, basically, I don't have the picture quite right here, but you have basically your, oh, you can't see this. I need some like talcum powder or something, But here, I'll do like Star Wars. Let's see here. Oh, hey. Seems like a waste of that, but I'll do it. Thank you. I wonder if this is going to work. No, that was kind of disappointing, but This thing doesn't even show up sometimes on camera. It's not a good frequency. That one's not very, it's not very sensitive to this particular color. Okay, anyway, so what I was trying to get at eventually is we have, all right, there's 3 waves, right? There is the incident wave and the transmitted wave, right? And the reflected wave. And we're not doing oblique incidence this time, we're doing just normal. So the incident, here's the incident wave, here's the reflected wave, and here's the transmitted wave, like that, all right? So one comes in, bounces back, another one travels through into the conductor, right? Now once the electromagnetic wave goes into the conductor, it has to satisfy the attenuated wave equation in there. But out in the linear media, it satisfies the plain Jane unattenuated wave equation, like the lossless wave equation, the one that has energy conservation out here. So we use the solutions that we had last class over here. We use the solutions we're just looking at this class over here. And they have to meet at the boundary. They have to satisfy these boundary conditions. Notice that you could have, in principle, free charge here, or even a surface current here. We'll find out that the particular wave we're looking at won't have that, but in principle you have to consider it. So here's the deal. This is like the mathematics of what I was just saying. Our incident wave and our reflected wave, notice that there is no kappa. No kappa, right? No complex wave number for those. We simply have the wave number K1 that is from the linear media. See that? K1, 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 K1. And notice here, it's in the z direction, so it's simpler than what we were doing last class because there's no, last class we were doing oblique incident, so I had to do the dot product with the wave vector and the position. But this time we're just going in the direct z direction and coming back. So to come back, we just do minus kz rather than kz. Kz goes to the right, minus k1z goes back again. And that's why there's a minus out here, because that takes care of the direction, okay, for the reflected. Oh yeah, these are the reflected. This might be, I think I might have missed a minus here. If I had to guess, I think there's a minus missing right there, okay? Pretty sure. So, and then the transmitted wave, on the other hand, now we're up against the complex wave number, right, inside the conductor, because these are attenuated, okay? But the mathematics, it's the same problem we worked last class. We just have to solve the boundary conditions, basically. So you get the free surface density 0 because the perpendicular electric field, so the perpendicular is in the z hat direction, but the electric field is in the x hat direction. So that's why E perp is 0, because the perp is the z direction and the electric field is given to be in the x hat direction. The magnetic field is also, and again, the magnetic field's in the y direction, so it's not in the z direction, so B perp is 0. Now, condition 3 gives that, I think I'm missing this is equal to 0 maybe. So this is the E1 perp, E1 parallel equals to E2 parallel. E1 parallel is, dudes, maybe I was wrong. Maybe there isn't. I feel like I should have a minus there. It really feels like a minus. Am I forgetting something? We're on like page 422 if you're wondering. Well, there is no, he doesn't have a minus for the reflected E. So the minus on the B but not on the E? That's weird. weird. Why is that? I don't understand that. I mean, the we're not talking about the z direction. We're talking about the x direction. Okay. I'm sorry. I've got the wrong idea. It's not the minus for the b. It's not because it's like z versus minus z. It's y hat versus minus y hat in the reflection process, and it just so happens in the reflection process that the reflected electric wave, it still has the same direction, apparently. I think these things come from carefully analyzing the boundary conditions, but obviously I haven't quite gotten to enough of the mathematical detail to chase down why that's a plus and not a minus. Like I'm saying that I didn't have a typo on the previous page, it really was plus. And if that is a plus, this is a plus. All right, and now this down here is from the minus in the magnetic field. Like in the reflected magnetic field, it had a minus on it, and that's carried over to here. Anyway, let me get to the end of the story here. So he introduces an exciting beta tilde, which is this particular mu1 v1 divided by mu2 omega times the complex wave number k tilde. And with the introduction of this, you can take your boundary equations and rewrite them as the blue and the red boxed equations. And then what you do is you can solve those like we did before to get these equations here for the reflected incident versus the transmitted incident electric field strengths. And that's very much like what we saw in the study of refraction, but beta tilde is complex, so it's a little bit more complicated. The most interesting case, of course, is for a perfect conductor, your conductivity is infinity, which makes the K2 formula go to infinity, which makes the beta tilde be infinite, which means that basically in the limit as beta tilde goes to infinity, this becomes a -1. So you get E tilde, the reflected is minus the incident complex phase, and this is 0. So in other words, if you have a wave going through linear media and it hits a conductor, right, then the transmitted wave, there is no transmitted wave. The conductor stops it. And the reflected wave has the same amplitude as the incident wave, but opposite. You know, it just bounces back with full amplitude.
Which is why metal's shiny.
Which is why metal is shiny, exactly. This is the physics of a mirror. Yeah. And whatever details I've been fuzzy on, you could easily fill in by the same kind of analysis we did last time. It's just a matter of sorting through the boundary conditions vis-a-vis the, the complex wave functions that we wrote down. You can do it. Yeah. So next time, we're going to look at waveguides, which is, and coaxial cables perhaps, I think kind of the same thing, but so like in the absence, in free space, right? We basically can't have, when we studied Laplace's equations before, they're kind of boring inside a conductor, right? If there's just a hollow space inside a conductor, what's the electric field in there? Can it be changing? Right. If there's no charge inside, then I think the electric field has to be constant, right? Because anyway. So but on the other hand, if inside the conductor there is another conductor, then all bets are off. Then you can have a non-trivial electric field because you've got like charge in the middle, and you can have things between. So like with the coaxial cable, you have the inside wire and then the outside, and then between those two you can have interesting fields. And so that's what we'll try to analyze next time, is like the waveguide problem. So anyway, thanks guys. Any questions? Actually, no questions.